When connecting new systems to an existing tower ground, you can bond a new number 2 conductor to one of the 3 existing number 2 conductors using a split bolt connector, provided certain conditions are met. Firstly, the existing grounding electrode system, including the 3 ground rods and their interconnections, must meet the requirements of the applicable electrical code and industry standards. Secondly, the split bolt connector used must be rated for the size and type of conductors being connected, which are number 2 copper conductors in this case. The connector should be listed or approved by a recognized testing laboratory such as UL or CSA. Thirdly, the split bolt connector should be installed according to the manufacturer's instructions. It should be tightened securely using a torque wrench to ensure good electrical connection. Fourthly, the connection point between the new conductor and the existing grounding system should be protected from corrosion. This can be achieved by applying an antioxidant compound to the connection and wrapping it with electrical tape. Additional considerations should also be taken into account. The new conductor should be bonded to the existing grounding system as close as possible to the point where it enters the tower. Also, ensure that the new number 2 conductor is of sufficient size to meet the grounding requirements for the additional systems being connected. Finally, periodically inspect the grounding system, including the new connection, for any signs of damage or corrosion and perform any necessary repairs or replacements as needed. By following these guidelines, you can ensure a safe and effective grounding system for the tower and the additional systems being connected. In detail, the grounding electrode system is a critical component of any electrical system, and it is designed to provide a low impedance path for fault current to return to the source. This helps to protect people and equipment from electrical shock and damage. The grounding electrode system typically consists of 1 or more ground rods, which are driven into the earth and connected to the electrical system. The ground rods must be made of a conductive material such as copper or steel, and they must be of sufficient length and diameter to provide a good electrical connection to the earth. The grounding electrode system must meet the requirements of the applicable electrical code, such as the National Electrical Code, or NEC, and industry standards. These codes and standards specify the minimum requirements for the size, type, and installation of the grounding electrode system. The split bolt connector is a type of electrical connector that is used to connect 2 or more conductors together. It consists of 2 halves that are bolted together, clamping the conductors between them. Split bolt connectors are commonly used to connect grounding conductors, as they provide a secure and reliable connection. The split bolt connector must be rated for the size and type of conductors being connected. This means that the connector must be able to handle the amount of current that will flow through the conductors without overheating or failing. The split bolt connector must also be listed or approved by a recognized testing laboratory such as UL or CSA. This ensures that the connector has been tested and meets the applicable safety standards. When installing a split bolt connector, it is important to follow the manufacturer's instructions carefully. The conductors should be cleaned and prepared properly before being inserted into the connector. The connector should be tightened securely using a torque wrench to ensure a good electrical connection. If the connector is not tightened properly, it can loosen over time, leading to a poor connection and potential electrical hazards. Corrosion can be a major problem for grounding systems, especially in harsh environments. Corrosion can weaken the conductors and connectors, leading to a poor electrical connection and potential electrical hazards. To protect the connection point from corrosion, an antioxidant compound should be applied to the connection and wrapped with electrical tape. The antioxidant compound will help to prevent corrosion from forming on the conductors and connectors. The electrical tape will help to seal the connection and protect it from moisture and other contaminants. The new conductor should be bonded to the existing grounding system as close as possible to the point where it enters the tower. This will help to minimize the impedance of the grounding path and ensure that fault current can flow quickly and easily back to the source. The size of the new number 2 conductor must be sufficient to meet the grounding requirements for the additional systems being connected. The grounding requirements will depend on the size and type of the systems being connected, as well as the applicable electrical code and industry standards. It is important to consult with a qualified electrician or engineer to determine the appropriate size of the grounding conductor. The grounding system should be inspected periodically for any signs of damage or corrosion. The inspection should include the ground rods, conductors, and connectors. Any damaged or corroded component should be repaired or replaced as needed. Regular inspection and maintenance will help to ensure that the grounding system is functioning properly and providing adequate protection from electrical shock and damage. Grounding systems are designed to provide a safe path for electrical current in the event of a fault. A fault occurs when there is an unintended electrical connection between a live conductor and ground. This can happen, for example, if a wire becomes loose and touches a metal object. If a fault occurs, the current will flow through the grounding system back to the source. This will cause the circuit breaker or fuse to trip, interrupting the flow of current and preventing electrical shock or damage. Grounding systems are essential for protecting people and equipment from electrical hazards. By following the guidelines outlined above, you can ensure that the grounding system is properly installed and maintained and providing adequate protection. Some examples of industry standards include the Telecommunications Industry Association, or TIA, Standard TIA 607B, Generic Telecommunications Bonding and Grounding for Customer Premises. This standard provides guidelines for bonding and grounding telecommunications equipment in customer premises. It covers topics such as grounding electrode systems, bonding conductors, and equipment grounding. Another is the Institute of Electrical and Electronics Engineers, or IEE, Standard IEE 1100, recommended practice for powering and grounding electronic equipment. This standard provides guidance on powering and grounding electronic equipment in commercial and industrial buildings. It covers topics such as grounding systems, power distribution, and surge protection. The NEC, or National Electrical Code, provides comprehensive requirements for electrical installations, including grounding and bonding. Specific articles in the NEC address grounding electrode systems, grounding conductors, and equipment grounding. It's important to consult the latest edition of the NEC for the most up-to-date requirements. Proper torque is crucial when installing split-bolt connectors to ensure a secure and reliable electrical connection. Over-tightening can damage the connector or conductors, while under-tightening can result in a loose connection that may lead to arcing, overheating, or failure. Torque specifications are typically provided by the manufacturer of the split-bolt connector and should be followed carefully. Using a calibrated torque wrench is essential to achieve the correct torque. The torque wrench should be applied to the nut or bolt of the connector until the specified torque value is reached. The torque value is typically expressed in pound-inches or pound-feet. After the connector is tightened, it's a good practice to visually inspect the connection to ensure that the conductors are properly seated and that there are no signs of damage. The connection should also be checked periodically for tightness, especially in environments where vibration or temperature changes are present. Antioxidant compounds, also known as joint compounds or corrosion inhibitors, are used to prevent oxidation and corrosion at electrical connections. These compounds typically contain a conductive filler such as zinc or copper particles in a grease or gel base. The conductive filler helps to improve the electrical conductivity of the connection and reduce the risk of oxidation. The grease or gel base helps to seal the connection and protect it from moisture and other contaminants. Antioxidant compounds should be applied to the conductors before they are inserted into the connector. The compound should be applied liberally to the contact surfaces of the conductors to ensure that they are fully coated. After the connector is tightened, any excess compound should be wiped away. Electrical tape is used to insulate and protect electrical connections from moisture, corrosion, and other contaminants. It is typically made of a flexible plastic or rubber material with an adhesive backing. The electrical tape should be wrapped tightly around the connection to provide a secure and waterproof seal. The tape should be applied in overlapping layers starting from the insulation of the conductors and extending beyond the connector. The tape should be stretched slightly as it is applied to ensure that it conforms to the shape of the connection. Different types of electrical tape are available for different applications. Some tapes are designed for general purpose use, while others are designed for specific applications such as high temperature or low temperature environments. It's important to select the appropriate type of tape for the application. The location where the new conductor is bonded to the existing grounding system can affect the performance of the grounding system. Bonding the new conductor as close as possible to the point where it enters the tower helps to minimize the impedance of the grounding path. Impedance is the opposition to the flow of alternating current and is measured in ohms. A lower impedance grounding path allows fault current to flow more quickly and easily back to the source, which helps to reduce the risk of electrical shock and damage. Bonding the new conductor further away from the point where it enters the tower increases the impedance of the grounding path. This can slow down the flow of fault current and increase the risk of electrical shock and damage. The size of the grounding conductor is determined by the size of the electrical system that it is serving. The grounding conductor must be large enough to carry the maximum fault current that could flow through the system. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the electrical system. These tables take into account the ampacity of the conductors and the voltage of the system. Using a grounding conductor that is too small can result in a high impedance grounding path, which can increase the risk of electrical shock and damage. Using a grounding conductor that is too large is generally not a safety hazard, but it can be more expensive. The grounding system should be inspected periodically for any signs of damage or corrosion. The inspection should include the ground rods, conductors, and connectors. The ground rods should be checked to ensure that they are still driven into the earth properly and that they are not corroded. The conductors should be checked to ensure that they are not damaged or corroded. The connectors should be checked to ensure that they are tight and that they are not corroded. Any damaged or corroded component should be repaired or replaced as needed. Regular inspection and maintenance will help to ensure that the grounding system is functioning properly and providing adequate protection from electrical shock and damage. In addition to the visual inspection, the grounding system can also be tested to ensure that it is functioning properly. Ground resistance testing is a common method for testing grounding systems. Ground resistance testing involves measuring the resistance between the grounding electrode and the earth. A low resistance value indicates a good grounding system, while a high resistance value indicates a poor grounding system. The ground resistance should be measured using a ground resistance tester. The tester should be connected to the grounding electrode into a remote ground reference point. The resistance value should be recorded and compared to the acceptable limits specified in the applicable electrical code and industry standards. If the ground resistance is too high, the grounding system should be repaired or upgraded. This may involve driving additional ground rods, replacing corroded conductors or connectors, or improving the soil conductivity around the ground rods. Improving soil conductivity can be achieved by adding water or a soil amendment to the soil around the ground rods. It's crucial to ensure that all electrical work, including grounding system modifications and connections, complies with the National Electrical Code, or NEC, and any applicable local codes. The NEC provides detailed requirements for grounding and bonding to ensure electrical safety. Some key NEC articles related to grounding include Article 250, which covers grounding and bonding in general, and provides requirements for grounding electrode systems, grounding conductors, and equipment grounding. Article 300.5 covers underground installations, including the burial depth for grounding conductors. Article 314 covers junction boxes and other enclosures, and specifies how grounding conductors should be connected within these enclosures. Local codes may have additional or more stringent requirements than the NEC, so it's important to check with the local electrical inspector to ensure compliance. Proper documentation of the grounding system is essential for future maintenance and troubleshooting. The documentation should include a detailed diagram of the grounding system showing the location of all ground rods, conductors, and connectors. Documentation should also include the results of any ground resistance testing that has been performed. The documentation should be kept in a safe and accessible location. Bonding refers to the practice of connecting non-current carrying metal parts of an electrical system together to create a low impedance path for fault current. Bonding helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. The NEC requires that all metal parts of an electrical system be bonded together, including metal conduits, metal enclosures, metal equipment frames, and metal water pipes. Bonding is typically accomplished using bonding jumpers, which are short lengths of wire that are connected between the metal parts. Bonding jumpers should be sized according to the NEC requirements. The bonding jumpers should be connected to the metal parts using approved connectors. The NEC specifies the types of connectors that can be used for bonding. The grounding electrode conductor, or GEC, connects the grounding electrode system to the electrical system. The GEC must be sized according to the NEC requirements. The GEC must be connected to the grounding electrode system using an approved connector. The NEC specifies the types of connectors that can be used for connecting the GEC to the grounding electrode system. The grounding busbar is a metal bar that is used to connect the grounding conductors together. The grounding busbar provides a convenient point for connecting multiple grounding conductors. The grounding busbar must be sized according to the NEC requirements. The grounding busbar must be made of a conductive material such as copper or aluminum. The grounding busbar must be mounted in a secure location. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. SPD work by diverting the surge current to ground, preventing it from damaging the electrical equipment. SPD should be installed at the service entrance of the building and at any sensitive electrical equipment. SPD should be sized according to the NEC requirements. SPD should be installed according to the manufacturer's instructions. Grounding and bonding are essential for electrical safety. By following the NEC requirements and industry best practices, you can help to ensure that the electrical system is properly grounded and bonded, which will reduce the risk of electrical shock and damage. When working on electrical systems, it's crucial to always de-energize the circuit before working on it. This can be achieved by turning off the circuit breaker or fuse that supplies power to the circuit. Before working on the circuit, use a voltage tester to verify that the circuit is de-energized. Always wear appropriate personal protective equipment, or PPE, when working on electrical systems. PPE includes safety glasses, gloves, and insulated footwear. Never work on electrical systems in wet or damp conditions. Water is a good conductor of electricity and can increase the risk of electrical shock. If you are not qualified to work on electrical systems, hire a qualified electrician to do the work. Electrical work can be dangerous and should only be performed by qualified individuals. Finally, remember that electrical codes and standards are constantly evolving, so it's essential to stay up to date on the latest requirements. Consulting with a qualified electrical engineer or inspector can help ensure compliance and promote safety in electrical installations.